So thanks for inviting me, and thanks to Demir and Reed for talking to me all week. Yeah, I wanted to talk to you a little bit about this business with counting uses of a theorem. This is joint work with Carl Mummer, who's at Marshall University. I've been pestering Carl about this for quite some time. And it really boils down to one question. This is the one that we were interested in. Can you prove RT24 with one use of RT22? The difficulty with this for most people is I'm already using terminology that's amazingly cryptic, right? So RT here is really just Ramsey's theorem, and you may or may not be familiar with that. So Ramsey's theorem says if you, for pairs and n colors, says that if you map the pairs of natural numbers into the number n, so the numbers between 0 and n minus 1, then you can always find an infinite subset of the natural numbers such that sort of the function applied to all the pairs taken from that infinite set are the same color. So they're monochromatic, right? So a lot of times we call the function of coloring, right? And we refer to the set as an infinite monochromatic set. I think if I draw you a picture, it'll help with this. So here's a formulation of Ramsey's theorem for pairs again. So when I'm thinking about a pair of natural numbers, right, I can just think of like all the dots on this graph, or the vertices on the graph as representing natural numbers. And then a pair is just an edge, right? So in this case, we've colored the edges with two numbers, one corresponding to red and one corresponding to blue. And what Ramsey's theorem says is if you've got a big graph like this, so essentially I'm truncating things a bit because I've decided that infinity is now 6. But if I do this on an infinite graph, then I'll be able to find some vertices. Here I've found 3, so that when I just look at the edges between those, they're all the same color. And so the infinite version is essentially the same picture. It's just that you have, infinitely many vertices around the edges, and then you get an infinite subset, and when you pop those edges out, you get a one-colored graph, which is just an amazing thing to find. So that's Ramsey's theorem for pairs. And one thing that has been known for a long time is you can certainly prove Ramsey's theorem for pairs in 4 colors with 2 applications of Ramsey's theorem for pairs and 2 colors. And you can carry out that proof in RCA naught. It's actually very, very straightforward. So now the natural question is, what do you mean by RCA naught? So that's the base theory for this program of reverse mathematics. And it's a subsystem of second-order arithmetic. So it has variables in it for natural numbers, and also for sets of natural numbers, but not for objects of higher type. And a variety of axioms, so arithmetic axioms, rather than giving you a complete list, I gave you some examples here, right? So if you add 0 to something, you get the same thing back. Basic arithmetic axioms like that. Induction restricted to sigma 0, 1 formulas, so formulas with a single existential quantifier. And then this recursive comprehension axiom that says essentially if you can compute a set, then it exists. So I should say a little bit more about what I mean by computing in this situation, right? And it's easiest, I think, to talk about recursive or computable functions. So I'll invoke Church's thesis here and just say that what I mean by computable is that there's some sort of deterministic algorithm that for any particular input number generates some sort of output, right? Actually, Fulton generates an output. Of course, when people first started talking about computability, computers were essentially people in white shirts with pencils that followed deterministic algorithms, right? But this is the same idea as Turing computable, right? So then you can say that a set is recursive if its characteristic function is recursive. And then the recursive comprehension axiom is essentially just saying, oh yeah, if you have a recursive characteristic function, then the set actually exists. And I am glossing over details here. I mean, the actual formulation of it in terms of second-order arithmetic is, of course, in a proof-theoretic setting, and so it's described in terms of equivalence of formulas, the equivalence of a phi 0, 1 formula, sigma 0, 1 formula, where those formulas might have parameters, so it's actually not just recursion, it's relative recursion. But this is plenty for us for right now. So what I was saying before was that if you work in this particular system in RCA naught, then you can prove Ramsey's theorem for pairs and 4 colors with 2 uses of Ramsey's theorem for pairs and 2 colors. And here's a sketch of the proof. Suppose that you're starting with your function that is 4 coloring the edges, so 4 coloring the pairs. And then you build a new coloring, right? And the new coloring says, well, I'll color at 0 if it's sort of if the colors are low, and I'll color at 1 if the colors are high, right? So you just split the colors into 2 groups, right? And this is where it's good that we talked about what RCA naught is, right? So this function is certainly computable from that function, and so RCA naught says that this function exists. And then if I'm applying RT22, right, I can find an infinite monochromatic set for this 2 color. So when I find that infinite monochromatic set, all of the edges will either be 0, 0 or 1, or all the edges will be in 2, 2, and 3, right? So either they're all low-numbered edges or all high-numbered edges. Right? Well, then I can construct a second color. And this time what I'm going to do is grab an edge, right? And if the edge was originally colored even, then I'll color it 0. If it was originally odd, then I'll color it 1, right? So I've got another 2 coloring here. And so I find a monochromatic set. And the claim is that this is monochromatic for my original function. Well, after I've done the first coloring, right, I'm either up here or down here, right? After I've done the second coloring, when I pick the monochromatic set, I'm on the left side or the right side, and that means that I'm in one of the corners, right? So now I have my set that's colored with 1 color. It's just 2 applications of Ramsey's theorem for pairs and 2 colors. So the way that I remember this question coming up is we were talking about this one time in Chicago, and I said, well, you can prove RT24 with two applications of RT22, and somebody says, so do you need 2 applications? And I said, well, that's an excellent question. So that was, what, 10 years ago? 8 years ago? It was quite some time ago.
5, 6.
Hmm?
I think 5, 6.
Oh. So yeah, that's the question. Can you get by with just 1 application of RT22, right? And so I have answers for you, right? And the answers are yes and no. Right? So it certainly depends on what kind of an axiom system you're working in, right? Because if your axiom system contains RT24 as an axiom, right, you can prove RT24 with no uses of RT22, right? You just write it down, you say it's an axiom, that's the end of the proof, right? But what I was interested in was proofs that aren't quite so silly. For example, RCA naught doesn't actually prove either of those things, right? So I was interested in the answers here, you know, relative to systems of axioms that look a lot like RCA naught. Well, the no answer is, it turns out that if you're working in this subsystem, I RCA naught omega, right, then there is no way to prove Ramsey's theorem for pairs and 4 colors with just 1 use, where I need to hedge on what I mean by 1 use of RT22, right? So we'll need to talk more about this because I need to tell you what an axiom system is and something about what I mean there by typical. But if you switch to the system that we've already looked at, RCA now, and it turns out that there actually is a way to prove Ramsey's theorem for pairs in 4 colors with just one use of Ramsey's theorem for pairs in 2 colors. So the proof that I just showed you is not optimal in the respect that it used RT22 more than it really needed to. So this is the business with one use is not enough, and that's where we want to work in this particular system. And this is an axiom system that was originally formulated by Colloquium. And I apologize, somehow I managed to forget to run LaTeX the second time, so my references will look peculiar. And the axiom system for RCA not omega consists of the following. Well, the first is this EHA hat crook omega, which is actually intuitionistic arithmetic. So this is like Haiti arithmetic here. And it's in all finite types. That's what the omega is about. So that tells me that not only do I have variables for numbers and for sets of numbers, but also for like functionals from sets of numbers to the sets of numbers and so on, right? I always get this backwards. The hat here means restricted induction, right? And the restriction on the primitive recursion is the crook. They throw on a choice scheme, so it turns out that in these intuitionistic arithmetic systems, usually you don't want to express your comprehension schemes flat out as comprehension. They do it as a choice scheme instead. So this is a particular sort of choice scheme. And the thing to notice here is this is an intuitionistic system, so it doesn't include full classical logic. It doesn't allow you to use the law of the excluded middle in every circumstance, right? Certain circumstances are still provable, but it's not universally true in this system. It's not a theorem, okay? When we're working in this system, we're also going to be interested in looking at these situations where we have essentially problems, and problems are things that are sort of A-E statements, where we have a couple of formulas that, so P1 here is supposed to say X is an example of our problem, and this part back here is supposed to say Y is a solution of the problem given by X. Okay. So the reason why we have to look at problems, or why we're interested in looking at problems, is because then we can look at Weihrauch reducibility. And this is an idea from computability theory. So we say that a problem Q is reducible to a problem P, essentially if there's a couple of functionals here, right, that make this diagram work this way. So the diagram's not terribly expressive, so let me tell you what's going on here. So I have these functionals psi and phi, and the idea is that if I take a problem of the Q sort, right, then psi is going to turn it into a problem of the P sort. So that if I take any solution to that problem, I have a way, uniformly, computably, to go back to a solution of the Q problem. So basically the idea is I can take Q problems, turn them into P problems in such a way that if I had a way to solve the P problem, I would automatically have a way to solve the Q problem. And this is all done in a computable fashion, right, and uniformly. Though one thing to notice here is that this is weak Weihrauch reduction. And so when you're using phi here to take yp back to yq, you can even remember what instance of the problem you were starting with before and use that information in the computation. So one thing that you can do is if you have problems like this, and you have this notion of Weihrauch reducibility, if you're working in the higher order reverse mathematics systems, you can actually formalize the whole notion of Weihrauch reducibility. So the fact that you got these functionals is actually something you can state in the language, and this is why we needed the higher order stuff, is so that we could say, yeah, I can actually find these functionals phi and psi, so that if u is a q problem, then phi of u is a p problem, such that any solution to the p problem gives me a solution of the q problem, computable from the original problem and the solution to the p problem. Okay. So yeah, basically all that this is saying is, yeah, q is Weihrauch reducible to p. It's a little funny because when you write the formula out this way, there's nothing that restricts phi and psi to computable functionals, right? But the fact that we're trying to discuss these things in this system where comprehension is sort of restricted to computable objects make it essentially Weihrauch reduction. So our formulation that we had before, I said I was going to show you that you can't prove Ramsey's theorem for pairs in 4 colors with one typical use of Ramsey's theorem for pairs in 2 colors. So let me finally tell you what I mean by typical in this setting. And that's, so we're going to say that we can prove Q with one typical use of P. And that means that if we have a problem here that's one of the Q problems, then I have some way of like constructing a term, right, that represents a P problem, where if I have a solution of that P problem, then I can find another term that's a solution of the Q problem, right? So when I'm making one typical use here, I'm not sort of using the P problem or the existence of the solution to the P problems in a really general setting. I'm just saying, okay, I'm just going to apply it to this one term. I'm just using it once. I'm using it in this particular case, right? Though in a sense that term's based on use, so it's generalized. And then the theorem that you can get out of this is if P and Q are reasonably nice problems, right, then this intuitionistic RCA dot omega proves Q with one typical use of P if and only if it actually proves that the Weihrauch reduction exists. So this is a pretty little theorem. I mean, it seems to make a very, very tight link between this computability theoretic notion and the idea that you can actually count the number of uses in a particular proof, right? I would give my usual disclaimer of that, in that this is like, this you can think of as being computability theoretic, but I'm not sure that this is really fair to think of it as being exactly computability theoretic, right? Because when you carry out that proof formally, right, you've done something a little bit different, right? So there's a nice link between these two sort of proof theoretic observations at any rate. So this is fishy, so I said nice problems, what do I actually mean? But it turns out that you want these problems, when you unwind the problems and look at the formulas, they need to be in this class gamma 1, right? Which that's as much as I'm going to say about gamma 1. And the reason why I need those in gamma 1 is because the proof is actually based on results of Kohlenbach that use modified reducibility. And I also want to give an ad here for work by Richard Kuiper, who's proved related results. They're really, really interesting. So let me tell you a little bit about the difference between Ricker's results and these results. So because we did the formalization here, we can get a biconditional, right? And Ricker's results do not use the formalization of the Weihrauch reduction, and therefore he only gets a one direction. The advantage of his stuff is rather than using the modified reducibility argument, He just invented his own functional interpretation in order to carry out the work. And as a result, isn't actually using modified reducibility, and so his stuff applies to a broader class of problems. He doesn't have to have stuff in the N1. Right? So I think that's like really, really interesting. And you can look for his work on the archive. I don't think it's published yet. So the corollary to the theorem, where I said there's this nice connection between proving things with one typical use and proving the Weihrauch reducibility, is that we get exactly what we wanted. That working in the subsystem, there's no way to prove Ramsey's theorem for pairs in 4 colors with one typical use of Ramsey's theorem for pairs in 2 colors. And you can think of the proof in like 3 steps here. The first step being, well, it turns out that if you just look on a computability theoretic, from a computability theoretic viewpoint, that Ramsey's theorem for pairs in 4 colors is not Weihrauch reducible to Ramsey's theorem for pairs in 2 colors. And that's in this article by Demir and his friends, which people often say Duray and his friends, because Francois comes before Demir in the alphabet, right? And I'm one of their friends, and Joe Maletti and Paul Schaefer are the other 2 people in that article. So you take that result, and then since this Weihrauch reduction does not hold, that means that I, RCA not omega, can't prove that it does hold, right? And basically the idea here is that there are no such functionals, RCA not omega is not going to prove that the functionals exist, right? I usually describe this by saying that the axiom system lies only by omission, right? It could be that it won't prove that the functionals do exist, so, but it never proves that functionals that don't exist do, right? And then you apply the previous theorem, right? This guy is, there's no proof that this guy is reducible to this guy, so there's no proof of this guy from one typical use of this guy. So when Carl and I first looked at this, I thought, okay, so that's actually interesting. For one thing, we were actually able to count uses of a theorem in a proof, right, which was not something that we'd had any success for previously. And I said, great, so now all I have to do is change this from intuitionistic systems to like systems that people really care about, right? So I want the law of the excluded middle back, right? Or not, right? Maybe there's a way to do this, right, with one use, provided that you use the law of the excluded middle somehow, right? And that turned out to be the correct direction of things. So it turns out that if you're working in RCA naught and you switch back to having classical logic now, right, you can prove Ramsey's theorem for pairs in 4 colors with just one use of Ramsey's theorem for pairs in 2 colors, right? This is a classical system, and you can guess, given that we couldn't do that in an intuitionistic system, that the law of the excluded middle must play an important role in this proof, as indeed it does, right? So here's the sketch of the proof. You know, start out with your 4 coloring. One of 2 things has to happen. Either you've got an infinite set where the coloring lands in a set of 2 elements, right? Or there is no such X. Right? One or the other. Right? So that's law of the excluded middle, right at the beginning. Now in those cases, in each case you do something slightly different. So in the first case, if you've got a set like that, well, pick it out, right? And I'm going to set some flag equal to 0 so I can refer to this later on, right? And if in the case that there is no such X like that, right, well then I'll just set X to be all of the natural numbers and I'll set my flag equal to 1 and proceed from there. So using the flags and my set X, because in either case I have my set X here to work with, I can define a 2 coloring. So how am I going to do that? Well, it sort of depends on which situation I'm in. So if I'm in this situation, right, so I know whenever I color two elements out of here, they're either going to be A0 or A1, right? Then I will color 0 or 1 depending on whether I'm looking at A0 or A1, right? And down here, if there is no such X, what I'm going to do is build my coloring sort of the way that I built the first coloring in the very first proof that we did, right? I'll either color 0 if I'm looking at low colors, or 1 if I'm looking at high colors. So now I get a monochromatic set for this collection, right? If it turns out that the flag was actually equal to 1, then that monochromatic set is going to give me an infinite set such that the function applied to them always falls within a set of two objects, right? Which contradicts the thing that set the flag to 1, right? So that can't ever happen. So it turns out that the flag has to be equal to 0. And in that case, the function here was just switching out between the two colors, and I have a monochromatic set, right? So I got my monochromatic set. There was only one coloring here, right? So there's only one application of Ramsey's theorem for pairs in two colors. And of course you can generalize this. It turns out that you can prove Ramsey's theorem for pairs in sort of an arbitrary finite number of colors with a single application, and the proof just becomes that much more messy, right? You just do a lot more cases, and the definition of the function here becomes more and more complicated. So initially I said, you know, we were looking at that proof of RT24 from two uses of RT22, and now we've got one that has only one use of RT22, and I said, you know, so this is more efficient, right? Well, it has fewer applications of RT22, right? If somebody asked me to read one of these proofs, this is the last thing that I want to do with my time, is to read proofs involving constructions like this. So I'm not sure that it's efficient from that viewpoint. I'm not claiming it's a better proof. It's just a different proof. And one that makes less uses of RT22. So I'll leave you with some references. And actually I wanted to flip forward and say one thing about this. So in doing this, in order to prove the theorem, we talked about one typical use of a problem to prove another problem, right? And we had this sort of technical definition, which in some ways to me seemed very artificial, right? And in other ways seemed perfectly natural. I wanted to prove a theorem, so I needed to write down what I meant and what I needed to get the result out, right? And that's what happened. Now, is this actually one use, or you know, what are other sorts of uses of theorems that we can look at, right? And those atypical uses, maybe even in the intuitionistic systems, we could reduce the number of uses if we allow uses of another sort. This is not something that I really know about. So that's the end of the talk.